In our previous lecture, we talked about, for second order autonomous systems, we talked about oscillatory behavior, which manifested itself through a closed trajectory, which we call periodic orbit, on the phase plane. Okay, namely, suppose that x1, x2, the board is our phase plane for our second order autonomous system. X that equals f of x, and x is our vector with the first entry x1 and second entry x2. Okay. Now, if this system possesses a periodic orbit, it means that on the x1, x2 plane, there is a closed trajectory, which we call the periodic orbit. And this behavior, in terms of x1 of t and x2 of t, can be seen through oscillations, okay, in individual state variables. And now, having defined that, which we call periodic orbit, and also a very special type of periodic orbit that is an isolated periodic orbit, we call a limit cycle. Okay, and we said that limit cycle cannot be generated. An isolated periodic orbit cannot be generated by a linear time invariant system. If you want isolation, you must have a nonlinear system, such as one dipole oscillator. And then we talked about methods to determine whether a given system x equals f of x possesses any periodic orbit or not. If the system is linear, then the condition is very straightforward, and it's an if and only if condition. All you have to do is you look at the eigenvalues. For linear case, this is x that equals a of x, so you look at the eigenvalues of the A matrix. Okay, and if those eigenvalues are, suppose that this is the complex plane, real, imaginary. Okay, if those eigenvalues are such purely imaginary pair, lambda 1 and lambda 2, then and only then the system produces periodic orbits or oscillations, or sustaining oscillations. Whereas for nonlinear systems, we don't have such an if and only if condition. Instead, we have a sufficient condition given us by the so-called Poincare-Bendixson theorem. And that theorem, or the conditions to be satisfied, listed in that theorem, were the following. Suppose this is your system, and for the system, you want to figure out whether it has a periodic orbit or not. Or in particular, whether it has a periodic orbit in some domain or not. So, okay, we consider this candidate domain M, that's a subset of R2, the plane, okay, and in that set, you check for the equilibrium points. There must be no equilibrium point inside M, or if there is, this M must be closely bound, by the way. If there is, there can be only one, okay? And if there is such an equilibrium point and a single equilibrium point inside M, then what you have to do is you have to go and obtain the linearization at that equilibrium point. You obtain A matrix, which is the Jacobian evaluated at equilibrium point. And if the eigenvalues of that A matrix both are here, excuse me, on the other side. If they are with positive real parts, okay. If they are here, okay, on the open right half plane, both of them, then that's one of the conditions is satisfied. And the other condition is that this M must be forward invariant. That is, any initial condition or any trajectory starting within M must remain in M for all future times. Okay. and so on. So such an n is called forward invariant. If n is forward invariant plus it satisfies that equivalent point condition, then the theorem stated that this region must contain at least one periodic orbit. Now, we're not going to prove that theorem, but instead we'll apply it to a nice, simple example. Okay, suppose that this is the second order system that we're given. x1 plus x2 minus x1, x1 squared, x2 squared. And x2 dot equals minus 2x1 plus x2 minus x2 times x1 squared plus x2 squared. Okay, this is our system, for which we will try to figure out whether it has periodic orbits or not. Show that there exists a positive number r such that the disk centered around the origin D, where it's a set of points that satisfy x1 squared plus x2 squared r squared. Basically, this is the set of points in R2 whose Euclidean distance from the origin is not larger than r. Okay, this is Euclidean distance squared, norm squared. Is forward invariant. Is is whether there is such an R. It could be a very large R, but a fixed R nevertheless, and for all initial conditions that we choose inside that disk, okay, or with Euclidean distance smaller than R, the resulting trajectory will never have Euclidean distance from the origin that's larger than R, or it will never leave this disk for all future times. Is forward invariant, okay? That is starting in D guarantees staying in D for all future times. Okay, so that's forward invariance. And then once that's shown, we will have one of the conditions for Poincare-Bendixson theorem satisfied, and then we can check also the condition regarding the equivalent points, and then combine those two conditions. If they both satisfy, we will be able to deduce that the system possesses a periodic orbit. Discuss the existence of periodic orbits using Poincare-Bendixson theorem. Note that once again the conditions are only sufficient. If they fail, it doesn't mean that the system doesn't have a periodic orbit. They may fail, and the system may still have a periodic orbit. So that's the difference between the nonlinear theorem and the linear theorem. The linear theorem is if and only if type. Okay. Now there could be different approaches to study this example or solve an example, but here is a more or less classic approach. Okay, when you have such a candidate to study its forward invariance, what you do is you compute its time derivative. Okay, so that's That's the very idea behind computing the time derivative total energy for the mass spring system, for instance. Okay, by looking at the derivative information, we can deduce some important qualitative information regarding the system. So let's begin by A. Let's define this function v of x. X is our state, x1 and x2, x1 squared plus x2 squared. Now that this function is no other than the square of the Euclidean norm. Okay. Now, let us analyze the evolution of the norm square v of x along the trajectories of the system. Okay. Now, one way to do that, or at least in principle one way to do that, is compute x of t, okay, x1 of t and x2 of t, plug in those solutions into this and obtain vx of t, and then analyze vx of t. Now the problem with that, which we repeated a couple of times, is that this nonlinear system, in general, we don't know how to write the explicit solution. Okay, so we cannot therefore perform an analysis exactly in the substance, so we have to go for quantitative analysis, so we have to do some qualitative analysis. And for that, what we do is we're gonna differentiate v with respect to time. So for this purpose, let us attempt to evaluate v dot. Okay, and v dot, by v dot, v. This x now replaces x with x of t, a solution, and then this v therefore becomes a function of time, and then you take the derivative of v with respect to t. Then. So v dot therefore is time derivative of v of x of t. Okay. Now what's v dot? Let's try to compute it. Perhaps we cannot obtain a useful equality for this, but we can obtain a useful inequality, okay, by carrying out the analysis. So v dot is d over dt of v of x, and x is a vector that has two entries, x1 and x2. Therefore v of x can be written also as v x1 of t, v x2 of t. Okay. So v function of x, function of vector, means v is function of two individual entries, x1 of t and x2 of t. Okay. So this equals what? So to compute that time derivative, what you do is you take partial with respect to x1, and then you multiply by x1 dot, and you do the same thing for the other argument, partial v partial x2 times dx2 dt. Note that this is no other than the inner product of two meaningful functions, let's say. We can write this as partial v partial x1 partial v partial x2. Okay, so here we have a row vector, and this multiplies the following column vector, x1 dot and x2 dot. Okay. This is no other than gradient of v transpose, because according to our notation or convention, gradient is always a column vector. So gradient transpose, and this is x1 dot, x2 dot. It's here. It's no other than the right hand side. Okay, so that's our f of x. Therefore, v dot, where v is a function of x, and x is coming from, or the solution is coming from this system, simply is the inner product of the gradient of v with respect to its argument x with the right hand side of the system, which is f. Okay, so, and this will be quite frequently encountered as we move along the course. Once again, we have v of x, okay, norm square, and to determine the behavior of, or evolutionary behavior of vx of t, what we do is we compute this time derivative. And the whole reason behind that is because we want to show, if we can, the forward invariance of a set, which is v of x less than or equal to some constant, some positive number. For that positive number large enough. So we have that for take v dot x equals the inner product of this vector, the gradient, with the right hand side of the system. So for the given v and f, this reads as following. The gradient is x1 squared plus x2 squared, therefore the gradient is 2x1 and 2x2. 2x1, 2x2, this is the gradient vector, and the right hand side is x1 plus x2 minus x1, x1 squared plus x2 squared, and minus 2 x1 plus x2 . Okay, now let's compute this inner product, that is this times that plus this times that. So this equals, this times that gives us 2x1 squared plus 2x1 x2 minus 2x1 squared, x1 squared plus x2 squared. Okay, and since x1 squared plus x2 squared is no other than v of x, we can use that shortcut and write directly here v of x. Okay, so this is this times that, plus we have this times that. Okay, which reads minus 4x1 x2 plus 2x2 squared minus 2x2 squared times x1 squared plus x2 squared, which is v of x. Now let's reorganize the terms. For instance, this will cancel with this, and here we would have 2x1 x2, and so that reads 2x1 squared minus 2x1 x2 plus 2x2 squared, and what we have is vx times, or minus 2vx times x1 squared plus x2 squared. Now x1 squared plus x2 squared is again vx, so these two terms produces a v squared x term. Okay, minus 2vx squared. Okay. Now what we know here is this is always, unless x is at the origin, this is always negative, this term. This sum is always positive, but here we have some indeterminate term. So let's try to deal with that term. And one way is to apply the following trick. So let's write this as 3x1 squared plus, and this as 3x2 squared. So to be able to do that, what we did, we added to this guy x1 squared, and we added to this guy x2 squared. But here we have an equality sign, so for this equality sign to hold, we have to also subtract at some point what we have added. And then we do that as follows: x1 squared plus 2x1 x2 plus x2 squared, okay, minus 2vx squared. Now this operates on that and gives us this. This now minus and operates on that and gives us this. And here minus 2x1 x2 is here. So these two things are actually equal. And then note that this is x1 plus x2 squared, which is never negative, but it has minus sign in front, therefore this is never positive. Since this is never positive, this whole thing is always less than or equal to this plus that, okay, this term removed. So we have 3x1 squared plus 3x2 squared minus 2vx squared, okay. We removed this term because it's always negative or non-positive. And we replace this equality sign with less than or equal to sign. And again, this is no other than 3 times v of x. 3v of x minus 2v of x squared. Okay. Now this is nice. So what we have here is v dot less than or equal to 3v minus 2v squared. Okay. Since everything is in terms of v, it's easy to interpret that inequality, and that interpretation will give us something very useful. Let's do that now. Okay. So, to summarize all that steps, this is the conclusion that we have reached. V dot, and V is the norm square, so it's something that's never negative. And V dot, its time derivative satisfies this. Okay, time derivative is always less than or equal to 3v minus 2v squared. Now, we cannot say much about the general positivity or negativity of this thing. First of all, v is never negative, therefore we can consider everything here v, and positive. Okay, so for v small enough, this will be negligible, and v dot is less than 3v. Okay, v dot is less than or equal to something positive. Therefore, it could be either positive or it could be negative, so that thing doesn't tell us much. But when v is quite large, this term will dominate, and v dot will be less than or equal to something negative. And that means for large enough v, v dot is negative, so that means if v is large, it has to shrink, it has to decrease. And that has some important consequences. So let's therefore talk about the meaning of this inequality. Okay. For that, to visualize it better, let's obtain the or visualize the function from v to 3v minus 2v squared. V versus 3v minus 2v squared. Okay. Now that v can never be negative, therefore we're not interested in this part of the plane. So, for v small, this will be negligible, and this thing will be more or less equal to 3v. Okay. And then as v increases, this term starts dominating, and then at some point they balance more or less the magnitudes of each other, and then after a while this will dominate the whole thing, and everything will be negative. And the overall curve looks like this. Okay. And And here, this point is where 3v equals 2v squared. And that's the point 3 over 2. Okay? So when v is larger than 3 over 2, 1.5. In other words, when v, remember v was the norm square of the state. When v is larger than 3 over 2, then v dot is negative. Okay. So v dot is negative in this region. Okay. And this region is the region where v is, or the norm square is larger than 1.5, or the norm, Euclidean norm is larger than square root of 1.5. Now, that means the following. Now let's translate v larger than or equal to 3 over 2. That set into our phase plane, okay, that is x1, x2 plane. Now v was x1 squared plus x2 squared. Therefore, v larger than 3 over 2 means that the Euclidean distance is larger than 1.5, square root of 1.5. Okay, so we have a circle with radius 3 over 2 square root. And this is 3 over 2 square root, okay. And we're talking about this region when we say v is larger than 3 over 2. Okay. And in the shaded region, okay, that is outside this circle with radius square root of 3 over 2, v is larger than or equal to 3 over 2. And when v is larger than or equal to 3 over 2, we are in this region, and when we are in this region, v dot, as this tail indicates, v dot is negative. Okay? V dot negative means, it's time to put negative, v is decreasing. Okay? Now v decreasing means, since v was the norm square is decreasing. Therefore, norm itself is decreasing because norm is always positive. Therefore, the Euclidean norm, or the Euclidean distance from the origin, when state is somewhere on the shaded region, must decrease. Okay, and that's what we need to eventually apply to the Poincare-Bendixson theorem. Okay, so in the shaded region, Euclidean distance of the state to the origin is decreasing. And that decrease will give us the forward invariance that we're trying to hunt down. Okay, so that was the crucial step, that observation. And from this point on, everything just follows very smoothly. All we have to do is just apply the Poincare-Bendixson theorem. So the interpretation of what we have observed or obtained here is the following. Hence, for any r greater than or equal to square root of 3 over 2, x0, the initial condition, that belongs to v x less than or equal to r squared, which is our closed bounded set candidate implies x of t remains in D for all future time. Okay. So let's restate that sentence also on the picture. This is our x1, x2 plane. Choose any r that's larger than that number. For instance, r equals 2. Okay. And then consider this subset, okay? Norm squared less than or equal to 2 squared 4. Now, if we start anywhere inside that disk, because Euclidean distance is decreasing, we should always stay within that disk. Okay. Okay. Why is that? Once again, suppose that you start inside this disk, and at some point you leave the disk. Okay. Okay, you start somewhere here and then you evolve after a while. At some point in time, okay, the state leaves that set. Now this cannot happen. Why can it not happen? It's because the following. Suppose that you consider this point, just where this trajectory crosses this border. Okay, at this point, consider this vector x of t. Now, what's the Euclidean distance at that of the state at that instant? Euclidean distance is the magnitude of this, or the length of this vector. Okay, the radius vector. Now, in order, just after a while, it's at t, just after, for instance, t plus epsilon, we're going to be here. Okay, somewhere. So clearly, here the radius is 2, and then after a little while, at t plus epsilon, let's say, after 0.1 second, this length, this radius is larger than 2. Okay? So between this point and that point in time, therefore, the radius or the Euclidean distance of the state from the origin must have increased. If Euclidean distance has increased, it means that at some point the derivative of that Euclidean distance must be positive, otherwise it cannot increase. But we have just shown that in the shaded region, okay, when r is greater or equal to this number, the derivative can never be positive. Okay, the derivative must always be negative. Since the derivative is positive, you can never, if r is large enough versus r equals 2, you can never cross that borderline. And that means if you start in this, you will always remain in that disk. And that means forward invariance. Okay. So, therefore, suppose that you start here, x0, and arbitrary condition is in that disk, and what we have just shown that you can do many fine stuff, but you can never leave the disk, you can never go outside. This is x of t. Now, that completes part A. Okay, that is, we have shown that a disk, if the radius is large enough, is forward invariant for our set, well, for our system. Now, as for B, now we have forward invariance, and eventually we're going to apply Fourier-Bendixson theorem. So what we have to do is we have to check for the possible equilibria inside our forward invariant set. Okay, so the next part is checking equilibria. Okay, so for that we're going to solve the equivalent point equation, that is f of x equals 0. F of x equals 0 means that x1 plus x2 minus x1 times norm of x squared. This is our f1. That should equal 0, and 2x1 plus x2 minus x2 times norm squared x must also equal to 0. Now we're going to try to figure out the pairs x1, x2, okay, for which this equation is satisfied. Now, to see the solution in an obvious way, let's write this two equations as a single matrix equation, where the matrix is a function of x, 1 minus norm x squared, x1, x2 equals 0, 0. Okay, here we have a matrix times a vector that equals 0. Now, if you compute the determinant of this matrix, this and that, they're the same thing. This square minus minus 2, therefore something non-negative plus 2, therefore the determinant is always positive. In fact, it's always greater or equal to 2. Okay. That means this matrix is always invertible. Invertible matrix times x1, x2 equals 0 means only one thing, and that means that this vector here must be 0, x1 and x2. x1, x2 equals 0, 0. So that means this has just one solution, and that solution is origin. Therefore, at origin we have an equilibrium point, and that equilibrium point is the sole equilibrium point of the entire system. Okay. This is the only equilibrium point. Okay. Therefore, our forward invariant set contains one equilibrium point. Okay. Now, since it contains one equilibrium point, what we have to do next is we have to check the eigenvalues of the Jacobian corresponding to the linearization at that particular equilibrium. So that's the next step. Linearization at the equilibrium. Okay. Partial f, partial x evaluated at the equilibrium f is here. Okay. If you compute that Jacobian at x equals 0, this is what you get. Remove the middle steps, but that's what you obtain. Now here we have the matrix. All we have to do is check the eigenvalues. Si minus a is s minus 1 squared plus 2. Hence, we have a complex conjugate pair with real part at plus 1 plus minus j2. Hence, the only equilibrium inside our forward invariant set satisfies the condition given by the Poincare-Bendixson theorem. Therefore, we can now close, or we can combine all the loose ends and invoke Poincare-Bendixson theorem to claim that this system must have at least one periodic order. Now, to summarize, throughout our analysis, we have collected the following peaceful qualitative information. D x1 squared plus x2 squared less than or equal to r squared. Well, if you're unhappy with this r being r, just choose something that's larger than 3.2, 3 over 2 square root, for instance, 2, then that's perfectly fine. Is forward invariant, provided that r is larger than this. D contains a single equilibrium okay, and that equilibrium is the only equilibrium of the system, that's the origin. And finally, the eigenvalue test at that equilibrium point gave us the following information. Eigenvalue of the linearization at x equals 0 satisfy this, that both real parts are simply positive. Okay, and that means all the conditions listed in Poincare-Bendixson theorem are satisfied. Hence, we can now invoke the theorem and claim that E contains a periodic orbit. By Poincare-Bendixson theorem.